you. So today we are glad to have Dr. Kasztenny from SEL. So Dr. Kasztenny is very well known in protection area. He has over 30 years of experience in power system protection and control. He has taught in academia over almost 10 years on different courses of the power system and digital signal processing. And then since 1999, he has joined industry as has been working on different relay manufacturing, working on design and support of the protection, control, and fault locating product. Dr. Kasztenny is a fellow of IEEE, IET Flow, and senior Fulbright Fellow, and distinguished member of the SEL. Dr. Kasztenny has been on so many standards and working group, including on the SEL Study Committee B5 and Western Protective Relay Conference program every year happening in Spokane. In 2019, Dr. Kasztenny received IEEE Canada Ziogas Electric Power Award. He got his PhD in 1992 and DSc in 2019. Dr. Kasztenny has over 222 technical papers, over 60 U.S. patent, and he is a senior editor of IEEE Transaction on Power Delivery. And also, I should say that when I started back in 2004, my master's degree in digital protection, I learned a lot from Dr. Kasztenny books on the digital protection. So that was my master's degree. So I'm sure we learned a lot today from him. With that, let's hand it off to Dr. Kasztenny. Yeah, back to you.
Okay, thank you very much, Said. I hope you could hear me okay. So thank you very much for the invitation. Today we are going to talk about transient-based line protection, and I'm going to focus on relay algorithms that are based on traveling waves. We will explain what traveling waves are and see how we could use them to improve protection. So what is it specifically that we are talking about? There are three ways to trip the breaker based on fast transients or traveling waves. The first one is the element that is based on incremental quantities. It's similar to distance zone 1, meaning that it uses local voltage and current only, without the assistance of any communications channel. We call that element TD21. TD stands for time domain, instantaneous or incremental quantity. The other way to trip the breaker is by using a scheme that we called traveling wave differential. So the ANSI number 87 stands for differential. TW we use to designate traveling waves. And finally, the third way that is very dependable is to use your classical POTT, so a directional comparison scheme with a communications channel that is based on very fast directional elements that are traveling wave directional and incremental quantity directional. Those protection principles are not entirely new. So if you look at the history of protection, you will realize that in the 70s and into early 80s, various manufacturers tried to implement those principles. Since then, those few relays have been decommissioned and kind of the industry, out of necessity, forgot about it. In 2017, at SEL, we introduced new, fully digital, very elegant, state-of-the-art implementations of those principles. So they are in the field for 6 years now. If you look at the volume of installed relays, we are talking about hundreds, if not thousands, of relay years, meaning one relay for 1 year, right? So say over 1,000 relay years of experience with very good track record in the field. I am going to argue, and this is why this story is important, is that those principles are an excellent solution for protection of networks with renewables. So by now you should be aware that, wind and solar inverter-based sources, they don't produce high currents, they don't output the 60 hertz components that allow, proper protection. And the transient-based relays, such as schemes based on traveling waves, they work on signal components that are independent of the source. I'm going to show and prove it to you, and that's why they are a good option for protecting those networks. Here are the, historical pictures. You could see that, the relays from the 70s or 80s, they were either analog using static technology or hybrids with a little bit of digital part in them. By necessity, they apply a lot of simplifications. They were designed without, state-of-the-art simulation tools. Some of it was the guesswork. And also those relays suffered from just poor hardware quality. They didn't have self-monitoring. They were based on, integrated circuits or even transistors. And what you see at the bottom, this is really an extremely high-end, very powerful relay hardware that implements those principles, adhering to the first principles without simplifications, with a lot of security built in. So before we talk how this stuff works, let me get your attention by showing how well it works. So what you see here is a record from the field. This comes from one of the utilities in southern United States. This is a 345 kV line that suffered a single line to ground fault. So you see that the C-phase current goes up after 3 half cycles, so cycle and a half. That current flightlines, meaning that the breaker opened the C pole of the breaker. The other two phases still carried the load current. If you look at the voltage and you know something about faults, you will realize that around this time, the arc was gone from the fault and the relay is reclosed here. The voltage comes back and the system is back to normal. When I show this picture, in various forums, people say, well, this is a nice simulation, but you forgot to introduce the breaker time. Obviously, the breaker will take another 2 cycles before it could open, right? And my answer is, no, this is not a simulation. This comes from the field. You see the breaker in action here. That breaker opened in cycle and a half because it was actuated practically instantaneously. So now if we zoom on the fault itself, I'm showing you the one terminal on the left and the other terminal of that line on the right. And you see the currents, voltages, all the wiggles, and so on. And when you look at the binary signals in the relay, you realize that the trip command asserted here, which is roughly 1 millisecond into the fault, right? This is phenomenal. By looking at less than 1 millisecond of the data, the two relays talking over a communications channel, they already know that this is an internal fault. The scheme that issued the trip command was the traveling wave differential. This is what it asserted. The traveling wave directional element saw that fault truly instantaneously in a few tenths of microseconds. The incremental quantity directional asserted here, so maybe 2 milliseconds. And if the differential didn't trip, the POTT would trip in less than 3 milliseconds. So this is the new level of performance for line protection. You will issue the trip command in 1 or 2 milliseconds. And if the breaker is rated for 2 cycles, and if it's tripped in 1 or 2 milliseconds, it will finish here. It will finish after a cycle and a half, and the whole fault lasts less than 2 cycles. It's gone, right? Now, how is it possible? So the first thing you have to have a relay hardware that is powerful enough to process all that information with extremely low latency. So just to give you an idea how the relay is designed, the currents and voltages are sampled and processed every microsecond. So every microsecond, we take a new sample, we not only convert it, so we know the value of current and voltage, we run a lot of calculations on it every microsecond. When it comes to communications between the relays, that's done over direct fiber, and packets are sent and received every 25 microseconds. That line that I showed was 40 miles long, so it takes a laser light in the fiber 350 microseconds to go from one relay to another. The relay processes the key logic every 100 microseconds. It has an output that could be directly connected to the breaker, so it's trip rated, that closes in 10 microseconds. And then if the relay is connected to a modern 2-cycle breaker, that breaker will clear in 1.5 cycles. So how difficult is it to design a relay like this? It's not very difficult, but it's challenging enough. The good news is that you follow the right principles and the outcome is guaranteed. You got a relay that works. This is the most powerful relay on the planet in terms of how quickly and how much information it could process with minimum latency. That alone is not enough, however, because you have to tell that computer which calculations to run in order to trip for internal faults and not trip for all the other conditions, right? So now it's the algorithm, is the how do we do it? So if you look at the case that I showed, the first millisecond, and here I am showing samples taken every 100 microseconds. So sampling rate is 10 kilohertz. The relays don't sample synchronously. So this is one relay, this is another relay. Before the fault, one current equals negative the other current. The fault happens, and those currents go up. And if you verbally apply a differential principle, you will conclude that this is an internal fault. But I told you that this relay doesn't sample at 10 kilohertz. It samples at 1 megahertz. So let's have a look at the same record from the field at currents that are captured at 1 megahertz. So one sample every 1 microseconds. So this is what you see. By the way, that pre-fault is not DC. This is only 0.2 milliseconds. So that short snippet looks like a DC, but it's a sine wave, right? And then the fault happens sometimes here, and the traveling wave came from the fault and hit the green terminal first. And what happened is that the current very sharply changed from this pre-fault value to this fault value. The same fault sent another surge of electricity towards the red terminal, but the red terminal, the first wave arrived here. So what is this ringing? The ringing comes from secondary cables in the CT circuit. There is capacitance there. The current transformers have capacitance in their windings. So then the ringing is noise, it's interference. And I picked that case on purpose to show you that, this is reality. Things are not ideal. There is signal distortions, there is oscillations, and every practical implementation needs to deal with it. But if you mentally reject those oscillations, you will see that the currents are doing this. Sharp change up, no change. Sharp change up, no change. Change down, no change. Change up, right? It's like a binary signal. So this is how I would like you to think about it. Those sharp changes in the current, we could call them traveling waves. And those traveling waves are like communication signals that are telling the relays where the fault is. So you could think of it, and it really is, that the spacing and polarities of all those pulses, up, down, they encode the fault location, and they encode whether the fault is internal or external. So that's the bottom line, because in the first maybe half a millisecond, we receive so much information that we actually could decode whether we should trip or not. That's how is it even possible that you could trip for a line fault with this speed, with a 1 or 2 millisecond speed. So, the basics to kind of understand traveling waves, or the prerequisites, if you speak the university lingo, would be, traveling wave propagation, reflection, transmission, things like termination effects, aerial and ground modes, Bewley lattice diagrams. So I will assume kind of that you have some knowledge of this, but when I go through the rest of the presentation, I will try to explain those concepts in simple words so you could keep up. So why do we have those sharp changes in the... So when the fault happened on a transmission line, what the fault does is it changes the voltage very abruptly from the value before the fault to something much lower, right? That's what the fault does. A fault collapses the voltage very sharply. And by sharply, I mean over a period of 1 to maybe 5 microseconds. So when you jerk that voltage that quickly, the distributed capacitance and inductance of that line, it needs to recharge. It needs to find the new equilibrium. So what happens is that you have a surge of electricity, this recharging process that now originates at the fault, but moves away from the fault as it travels. And that surge of electricity travels at nearly the speed of light. It's commonly referred as a traveling wave. And you could think of that stuff like falling domino blocks. So imagine that this distributed inductance and capacitance is like domino blocks, and the fault, pokes them, and they keep falling. And as they keep falling, they move at a certain speed. How fast is that speed? Well, it's pretty fast. It's, 98% of the speed of light. But that's, if you look at the towers are roughly spaced 300 meters apart in high voltage networks, or 1,000 feet. So it takes 1 microsecond for that surge of electricity to move from one tower to another. So if for a long line, it will take hundreds of microseconds to move from the fault and reach the terminal, right? So this is how the traveling waves are born. They are born because the fault voltage collapses sharply and sends the surge of electricity away. So this is that very first surge that came at one terminal and the other terminal. The other sharp changes are reflections, because those waves now bounce and reflect off the buses and other discontinuities. So here is an old black and white video that I borrowed from AT&T. This is a mechanical simulator of a long line And the gentleman is causing a disruption, so think of it as a fault. And this is how that wave propagates. It's really like a wave in a pond if you drop a pebble or a stone in it, right? So the wave starts, it moves away from the point of disruption, then it reaches the shore, it reflects off the shore, and the waves keep bouncing and eventually overlap and blend, and you cannot tell anymore what's going on, right? So what is a traveling wave? I want you to remember two definitions. One is that it's a surge of electricity that travels at near the speed of light, and it's born or caused by sharp change in voltage, such as a fault. And sure, you could write Maxwell equations, but this is just mathematics. From the signal processing point of view, traveling wave is an abrupt change in the relay current or voltage. So let me show and identify traveling waves in that plot. This is a traveling wave. This is a traveling wave. This is a traveling wave. So each time I see a sharp change from one level to another, that's a traveling wave. So the first thing we have to do is have a signal processing tool to catch those waves. So what we use in our relays is called a differentiator smoother. That's a very simple IIR filter with a bunch of ones and bunch of minus ones. So those of you who studied signal processing, that's the first order Walsh filter. We use differentiator smoother because a few decades ago, Dr. Schweitzer, he developed a fault locator based on traveling waves for DC line somewhere in California. And at that time, he looked at the literature and he found that the early digital radar systems, they use differentiator smoother because it's a good edge detector, right? So if you have an ideal step in the current and you pass it through this differentiator smoother, it will give you a triangle-shaped wave at the output. What is the meaning of that triangle? That the time of the peak, notwithstanding the time delay, that is the group delay of that filter, identifies the arrival time of that wave, and the peak of that output identifies how much that signal changed. Real traveling waves are not ideal steps. They could lean a little bit like this because of the dispersion. So the output is not a perfect triangle. It's smoothed a bit, but nonetheless, the time of the peak is the arrival time, and the value of the peak tells me how much that signal changed and whether it went up or down. So this is it. If you look at the papers today, you will have everything available used to process the signal to extract traveling waves, from wavelets to neural nets to whatever catches your fancy. My personal opinion is that there is marginal improvements if you go for any, let's call it more modern or sophisticated signal processing method. Differentiator smoother works just fine. So here is how it works. This is the very first wave in my field case. There is a lot of ringing, and this is the output. So is it a pure triangle? Of course not. But I could clearly see the time of the peak, the 10 microsecond notwithstanding, that's the arrival time. And I clearly see that the waveform moved up because the output is positive. And the waveform moved up by 1,000 amps. Is it true? Yes. If I put an ideal step here, this is what the ringing is around that value. So my waveform moved from -100 to positive 900 amps. So it moved up by 1,000 amps, right? So that output tells me there is a wave it arrived here, and the wave is a change from low to high by 1,000 amps. And yes, there is some distortions in that output, but they are much lower than in the initial waveform. So that's how the differentiator smoother attenuates those nasty ringing signals that I have in the field. So when I process my two currents, local and remote, with the differentiator smoother, I will have first wave at the green terminal, second wave, third wave has a negative polarity. I could measure the time difference between all those waves. So this is how I decode that initial information. And what I decode in it is polarities. So for example, the very first wave at the green and the very first wave at the red terminal, they are of the same polarity. Note arrival times. So I know that the red terminal first wave arrived precisely so many microseconds after the first wave at the green terminal. And I decode magnitudes. So I know that the first wave at the green terminal was roughly 900 amps, right? So this is the information I extract. So how do we use this information? Let's start with the double-ended traveling wave fault locator. So now assume that this is terminal 1, this is terminal 2. The gentleman is going to cause a fault at this location. And watch the wave, right? Excuse me, I need to. So a fault happens. The first wave is going to arrive at T1, and then T2 will see the first wave, right? So there is a time difference in arrival. So, you know, a very simple math is like this. This is, by the way, Bewley diagram. So the time goes down. This is the fault. This is one terminal. This is another terminal. A fault happened, and it sent a wave towards the S terminal. That wave arrived at TS. It traveled between the arrival time and the fault time, and line length divided by the propagation time, so end-to-end propagation time, is speed. So distance is times speed. This is your high school equation. A bus leaves the station, travels at 60 miles per hour for 1 hour. How far did it go, right? I have two unknowns here. I don't know the fault time. I only know when I receive the wave, and I don't know the distance. But the same fault sent the traveling wave towards the other terminal, and I write a second equation that the distance to the other terminal, which is total line length minus distance to the first terminal, is the travel time for the second wave times speed. Two equations, two unknowns. I solve for the distance, and here we go. From the difference in the arrival times between one terminal and another, and the total travel time, which is a fixed number for that line, and the line length, I could calculate the fault location with huge precision, with a precision to the tune of, 500 feet. So how well? So that's the fault locator. Let's talk about protection. So let's start with an external fault. So assume that terminal 1 is here, terminal 2 is here. The CTs are looking away from the bus towards the line. And the fault happened behind terminal 1. So again, let the gentleman cause a fault and watch the wave. The wave will start and it will enter, travel through, and leave the line at the other terminal, correct? It's just like a bullet going through a, space. That wave didn't change polarity. Say it was a positive wave. However, because the CTs are looking at each other, if that CT measured positive surge, that CT will measure the negative surge. Not because the direction of the surge changed, it's because the direction of measurement is opposite, right? So this is a picture for external fault. That fault happened behind the yellow terminal. So the wave first hit the yellow terminal. This is the wave. Then that wave traveled for the propagation time and left at the other end of the line. But because the CT at the other end of the line looks in the opposite direction, what came as positive leaves the line as negative, right? When I go to internal fault now, the very first waves will be of the same polarity. So wave goes to the left and goes to the right, and two CTs will register the same polarity of the wave, even though they will receive those waves at slightly different times, right? Because that fault may be closer to one terminal versus another, so there is a different travel time from the fault to one terminal and from the fault to the other terminal. But the polarity that will hit both terminals is the same. So this is the picture for an internal fault. You know, the fault is internal, one terminal saw a wave, the other terminal saw a wave. But just because we see a wave, it doesn't mean that the fault is not external. So what the relay does says something like this. I received the wave, but maybe it came from the outside. So let me see if that wave is traveling through the line and if it's going to leave at the other terminal around after the line propagation time. So the wave came but never left, and the same for the other terminal. The wave is there, but it's not leaving at the yellow terminal. So that tells me that this cannot be an external fault. So the logic or the principle, if I were to put it in English rather than in math or logic diagrams, is something like this, that, you know, we kind of follow the Kirchhoff's current law, meaning that traveling wave in is traveling wave out for external fault, except we know that that traveling wave out will happen after the end-to-end travel time, right? For external faults, what comes in will come out after a propagation time with flipped polarity. And for internal faults, the very first waves will be of the same polarities and they will appear, they will be time-spaced less than the line end-to-end travel time. So when it comes to mathematics, the relay gets the first wave, then waits for the line propagation time and says, is this wave coming out? So for internal fault, it's not going to come out. For external fault, this wave is passing through the line, so it came here and it's leaving here, right? So the relay creates the operating signal as the sum of the very first waves, and it creates two restraining signals. One assumes that the wave came at local and it's leaving at remote. And the other hypothesis is that the wave came into the line at remote and is going to leave or exit at local. And then the relay uses the higher of the two restraining quantities for restraint. So let's see how it works. We have our system, and these are the very first waves at one terminal versus another for an internal fault. So the first thing we see is that the waves came 41 microseconds apart. The end-to-end travel time is 227 microseconds. So the first thing we do is we calculate the fault location from, say, terminal 1, and we get 59%. So immediately, from the very first waves that we caught, we know with high confidence and high precision where the fault is. We also know that, the very first wave at one terminal was roughly 700 amps, and the other terminal was 800 amps primary, right? So the part of the logic is we say the traveling wave at the local and remote, they must be higher than some factory threshold. So we actually saw a wave locally, we saw a wave remotely, and the sum of the very first waves, the operating signal, is also significant, is higher than some threshold. So that's the level condition. We don't trip from that signal, but that's a first step towards deciding to trip. So let's look at the parallel line. The parallel line shows a very similar pattern. The first waves at both terminals are of the same polarity, but here immediately you will see that what came in at the green terminal is leaving with opposite polarities at the red terminal. What came in at the red terminal is leaving with opposite polarities at the green terminal. So how does it work? So the fault is here. That fault sent roughly 500 amps of surge current towards terminal 2. When that current hits the bus, based on the termination effects, it sends surges of electricity into each line connected to the bus. We have 1, 2, 3 other lines connected to this bus. So the way the mathematics works is that if 500 amps hit that bus, some of it reflected back, and 240 goes here, 240 goes here, and 240 goes here. The CTs are looking into the line, so if this was positive 500 amps, this is negative 240. What will happen to this 240? It will travel along line 2, and after 227 microseconds, it will show up at terminal 1. Now, you may say, we got ourselves an amplifier. How come the current here injected into this line is 240 amps, but when it arrived, it shows at something higher? Well, this is so-called termination effect. So 240, it was what was launched, but then the 240 was received, some of it was reflected, and the CT measures the sum of the two. That's why it's higher. Can I see that in the record? Absolutely. So the blue terminal, which is T2, saw the first wave to the tune of 240 amps. After 227 microseconds, those 240 amps showed with opposite polarity at the green terminal, which is T1. So this is what came in, and this is what is leaving. The same fault, so we calculate the restraining quantity as the difference between the two, and we get what we get, right? The same fault sent the same 500 amps towards terminal 1. So what happens here? It splits into 4 lines, and we have 200 amps launched at T2, T1, and traveling towards T2. Because of the termination effect, the CT here will measure a higher value. That's all correct. And again, the surge had a polarity that didn't change, but this CT looks this way, this CT looks this way, so whatever was negative here, it will show up at positive here. Can we see that? Absolutely. This is your 200 amps that hit that CT first, and 227 microseconds, that value showed up as 300, leaving at the other end of the parallel line. We calculate the restraint and we get this. So for the parallel line, the sum of the first wave, which is the operating signal, is 440. The restraining signal is 620, which is less than that. And based on this condition alone, the relay will not trip, as it shouldn't, right? This is the parallel line that doesn't have a fault. In the protected line, the operating signal is over 1500 amps. The restraining signal is 1100 amps. The condition is satisfied, and the relays on the protected lines will trip as they should. What is the amount of information I need in order to decide to trip? Just over 227 microseconds. That's how quickly I know that this is an internal fault. The other security condition that we use is related to voltage. So let's look at this AT&T video from the 50s or whatever. And now pay attention to the polarity. So the gentleman is going to move that model either up or down, and the waves will follow that polarity, right? So he is twisting it this way, up, and what we receive, up. The wave at the CT went from this value up. So the polarity of the wave follows the polarity of the disturbance. There is no other way. It must be this way, right? You cannot push something to the left and expect that it will respond by moving to the right, right? That's what I mean by saying that those traveling wave characteristics are very difficult to corrupt. So if I look at the voltage, this is the instantaneous voltage at the moment of the fault at the left terminal and the right terminal. There is a voltage drop across the line. So I could approximate it with a straight line. So if the fault was here, this was the pre-fault voltage. If the fault were here, this is the pre-fault voltage. We know where the fault was. We know it from the arrival times of the very first waves. So I know what the fault was. I know what the pre-fault voltage was. So now, if the pre-fault voltage was positive, the way I'm showing it, the fault will collapse that voltage from certain positive value towards zero, right? That's what the fault does. The fault is shifting the voltage from whatever level towards zero. So the logic is like this. If the voltage at the fault point was positive, the change in voltage is negative, the surge in the current is negative, but because the CTs measure towards the line, they will see a positive current. So the logic is positive voltage before the fault, positive traveling wave current. So what we do here is really we use the traveling wave current and we check the polarity of that current against the polarity of the pre-fault voltage. They must agree, or else this is not an internal fault. So effectively, we are doing 2 out of 2, right, for security. The other security features we have is we check our own assumptions. So we build a relay based on certain assumptions. One of them is that traveling waves are step changes. So we measured here that the step change was roughly 1000 amps and it occurred at this time. But what the relay measured is not a step, it's this ringing. So the relay calculates the difference between the ideal step that we expect based on the measurement of the traveling wave, and the waveform as it was recorded by the relay. If that difference is too much, the relay will say, I don't want to take a risk. I'm not going to trip. Let something else trip. Okay. Here is another security condition. If you have a lightning strike nearby, the power conductors act as antennas and they will pick up that signal. But because they are located approximately the same distance from the lightning strike, the signal in the A phase, B phase, and C phase will be very similar. It will be so-called zero sequence mode or ground mode. So here I plotted the alpha or aerial mode for a fault and the zero sequence mode for a fault. Normally, the zero sequence mode is significantly lower than the aerial mode, like in the picture. If this is the case, the scheme is allowed to operate. If the proportion is flipped, the ground mode is high, then the scheme says, there is something fishy here. I'm not going to take the risk. I'm not going to trip. Let something else trip, right? So this is how we build security. Because when you think about it, signing up to build a relay that trips in a millisecond and never misoperates, it's a tall order, right? So nobody wants to embarrass themselves. There was a lot of thought put into security. How well does it work? This is the zoom in. This is when the traveling wave differential asserted. Less than a millisecond, actually around 0.7 milliseconds. So this is how much the relay knows when it trips. Normally you would say, tripping so fast is absolutely crazy. It will never end up well. And if you said that, you would be right if you assumed that the relay tries to measure the magnitude of the 60 Hertz component and use that information for tripping. Those relays don't measure 60 Hertz component. What they measure is the polarities and timing of all those pulses, and that signal carries so much information in the first millisecond or half a millisecond that it's perfectly secure to make a tripping decision based on that information. So this is your innovation. This is the novelty. Looking at the same fault through a lens that is so much better than what the relays used to do. And because of that, being so much faster. Now, let me ask you this question. When the fault happened at tower 127 on the line, does the source know that there is a fault? Absolutely not. That surge travels 1 microsecond per tower, and it takes microseconds to a fraction of a millisecond for that information to even arrive at the source. Those signals are totally independent of the source. What drives those signals from the energy balance point of view is the energy stored in the transmission line prior to the fault. This is what fuels those signals to occur and then to travel like the falling domino blocks along the line. Where I'm going with this, I'm trying to prove to you that if you utilize these signals for protection, your protection is totally independent of the source. So this is why we could claim that those schemes are not only fast for the sake of speed, they are fast, and by being so fast, they operate for all sorts of sources, including power electronic inverter-based sources. This is how fast the differential operates. It's sub-millisecond for short lines. It's slightly slower for longer lines. The operating time is fixed, and that operating time is just the reflection of how long does it take for surge of electricity to travel on a long line, and how long does it take for a pulse of laser light to travel from one relay to another. That's all there is to it, right? So we have a long line, long piece of fiber. That's why for a line that is 200 miles long, it will take 3 milliseconds to operate. It has nothing to do with fault resistance or fault location. The other principle, and I have to write it, wrap it up, is the directional. So when the voltage collapses, it sends the current that is proportional. The relationship between the two is the characteristic impedance. That's your 350, 370 ohms for an air-isolated line. And they travel together, right? So if you had a PT or CT at each tower, you could measure it, and you will see how they move at the speed of light from the fault towards the terminal. At the terminal, in a substation, you have a CT that measures into the line. That's why the relay measures negative current. So then the rule is very simple. If the voltage changed abruptly in one direction, and the current changed abruptly in a different direction, and this is what the differentiator smoother gives me. So one sees a negative pulse, the current sees a positive. That must be a forward event. If they move together, so one is negative and the other is negative, or the other way around, that must be a reverse. So that's it. That's the entire theory, to build an extremely fast directional element that operates in, 50 microseconds. Here is the current and voltage for the field case, and you will see that the voltages are much worse. There is much more ringing in the voltage signal because voltages are high impedance terminated. The voltage changed down, it went down, but in the process, for in a form of oscillations, it went up. But if you look at, say, 50 microseconds, you know that it moved from this level to this level. The voltages are smudged. Here I see the second wave. In voltages, I don't see the second wave. So voltages are, we stay away from voltages because of that particular reason. But the traveling wave directional is secure. Otherwise, we wouldn't have it. It may not be fully dependable, meaning that with some PTs, voltage transformers, the voltage signal could be so bad that the directional element is not going to assert. That's perfectly fine because we still have the other directional element that works on incremental quantities. That's a different lecture that maybe we could deliver one day in the future. So that's pretty much it, the differential and directional. If I were to sum it up, a true traveling wave-based protection is based on mutual polarities and arrival times of traveling waves. It's not the 60 hertz, it's not the magnitude of those signals, it's did they move up or down and how quickly precisely they arrive one against the other. The traveling wave protection applies to power lines. Now, you could take the very high frequency signals and use them to improve protection of transformers and other apparatus, but that's a different story. We are talking about line protection primarily when we say traveling waves. Current transformers are good enough. I mean, I show the cases when there was a lot of ringing far from perfect, but it's good enough to attempt protection. Voltage transformers, not so much. There are poor sources of voltage information at those frequencies. Our implementation stays away from voltages. Those traveling waves dissipate quickly, so you catch the information in the first millisecond and you trip, or you will never trip, so you need other principles for backup. But on a positive side, those signals are independent of the source, and you will be working just fine, whether it's a synchronous generator driving that fault current or an inverter connected to a solar panel driving that current. And that's a big thing these days in systems with, renewable energy. As I said, those traveling wave features, polarity, arrival time, are less or practically independent on system conditions and sources. The polarity arrival time, I call it binary information. You cannot hit something to the left and have it move to the right. It's physically impossible, right? So the polarity is a very robust feature that is very difficult to corrupt. The same with the arrival time. If the wave moves at 98.1% of the speed of light, that's how fast it moves. That wave is not going to get tired and take a break and wait, right? If it moves at the certain speed, it's guaranteed to move at that speed on Tuesday and Wednesday and this year and next year, right? For a given line. So the arrival times are solid pieces of information that are difficult to corrupt. And things like polarity and arrival time, they couldn't care less about things like fault resistance, for example, right? The traveling waves are easy to analyze once you learn the process and you learn the basics. If you hate analyzing 60 Hertz systems because they involve things like matrices and complex numbers, you should love the traveling wave analysis because there are no matrices and there are only real numbers, right? That's a surprising thing of looking at the same apparatus at 1 megahertz versus, 60 hertz. Those schemes that we have released in 2017, and they have, practically speaking, perfect security record. We do not have issues with those schemes. Now, we put a lot of work to make sure that there is no embarrassment, that, we could put something on a table that trips in 1 millisecond, and yet it will not misoperate, right? If you want to study more, I would recommend these two papers. So the top two are papers. The last one is the appendix in the instruction manual. It's the signal processing and operating principles appendix. It has detailed information that is good enough to either model what the relay does or devise test signals for testing those new principles. So for anybody who wants to kind of play, improve on, understand, and they want to do it through modeling and simulation, that annex or appendix is golden. So I will stop here so that we have at least some time for questions. If you want to follow up with me directly, you could email me. We are very proud of that technology. We are ahead of everybody else, and it works like a charm. So with this, let's see if we have any questions. I think you're on mute.
Yeah, fine. Yeah, thank you, Bogdan. That was really informative. So in the classes, usually we talk about this, but always nice to hear things from people who actually implement that. So with that, you guys maybe have maybe let's go to online people. So anybody online have a question? May have? If yes, you may unmute yourself and ask your question. No? Okay, if you have a question, let me know later on after we're done with the people in the room. So anybody in the room? So you may have a question? Yeah, go ahead.
Okay, so I actually have three questions. So the first one is, what's the difference between the 87 traveling wave and the 50 instantaneous overcurrent or the 27 under voltage in terms of speed? Because like I mean, conventionally we have the under voltage and the overcurrent, which is the basis for the traveling wave, because everything you measured is based on overcurrent or under voltage. That you use to implement the traveling wave. So
let me correct you. In high voltage transmission systems, you don't protect anything with overcurrent and under voltage. Those principles are not powerful enough to tell you where the fault is. So, you could have a time coordinated overcurrent in distribution, and you could trip on under voltage, but for different reasons than, to protect against the short circuit. In transmission, you use impedance protection or distance protection, differential protection, and the pilot schemes that compare directionality at both ends. And the way to understand it is as follows. You cannot use overcurrent because you may have an internal fault and the system is weak or the resistance is high, and you get, say, 1,000 amps only. At the same time, you could have an external fault that will give you 2,000 amps. So you cannot make a decision. In order to not to trip for external faults, you will have to set your overcurrent above 2,000 amps. And in order to trip for internal fault, you will have to set it below 1,000 amps. So it's impossible. You cannot be above 2,000 and below 1,000. There is a narrow application of so-called high set overcurrent for line protection, but that's not really even worth mentioning. But if I rephrase your question, I think one way to rephrase it is, what's the difference between a principle that looks at 60 hertz voltage and current and a principle that looks at traveling waves? And the difference is that in order to measure how much 60 hertz current you have or voltage you have to watch that signal for between half a cycle and a cycle. If you try to guess how much 60 hertz current you have by watching that signal for less than half a cycle, you could be making such a gross mistake that you shouldn't be basing your protection based on that. So the protection principles that work on 60 hertz, they are inherently slower. The traveling wave information is packed in the first millisecond of the fault. So you have to sample fast. You have to know how to extract that information. You have to know how to use that information. But you have all the information you could get within a first millisecond. And it's a different type of information. So, that's the key difference here, that, with the new technology, we could sample and process things so fast that now we are able to build protection based on totally different spectrum, frequency spectrum in the input signal, use different pieces of information and make that protection not only fast, but also independent of the source. right? So that would be my answer to this.
My second question is: can you briefly explain why this protection is good for inverter-based network? Because I think you mentioned something like that.
Yeah. So when you have an inverter source and you put a fault there, the currents are low, distorted. The negative sequence doesn't behave. Simply, if you put a fault close to an inverter, that inverter is not going to push a lot of current for a number of reasons. I mean, the first one is that the control algorithms throttle down that current in order not to burn the semiconductors. The second one is there is not enough energy stored in the capacitor on the DC side of that inverter to give you a lot of current. So you don't have 60 hertz current to work with. Traveling wave is fueled, it's powered by the energy stored in a network prior to the fault. So you could have no sources, or you could have one source that is extremely weak. That source energized the line to have a pre-fault voltage. And because that line is energized, you will get your traveling waves. So the signals that this protection is using, those signals are independent of the source. And let me prove it to you the following way. You have a fault. It takes 100 microseconds for a wave to arrive from the fault to the terminal. And the source is another so many miles away. So when the traveling wave arrives at the terminal, the source doesn't know there is a fault because that surge of electricity didn't arrive yet at the source. And if you ran, EMTP, PSCAP, RTDS simulations, and you pay attention to the timing, you will see that when the fault happens, initially, none of the elements of the system knows there is a fault because it takes so many microseconds for that disturbance to arrive at the terminal and even more time to arrive at the source. So, this is just signal features that are truly independent of the sources. And if so, they work the same with IBRs and synchronous generators. And because they work well, then they work well with IBRs.
Any more questions? Anybody else? Maybe we have time for one or two more questions at most.
Okay, well, maybe I can.
Yeah.
So before the invention of the traveling wave, so what's the difference between the protection element in the relays back then, the differential protection elements in the relays back then, and the traveling wave differential protection, and how fast? So what's the difference between the speed of these elements, and are they used in parallel, or is there like a hierarchy to the usage?
So they are used in parallel. And there's the fundamental frequency-based protection. So the one that is based on 60 hertz. If you have a lot of short circuit current, strong source, closing fault, say a zone 1 distance element could operate in half a cycle. More typically, it will be 1 cycle, or maybe bleeding into cycle and a half. If you have a weaker source, cycle, 2 cycles would be a typical time. If your protection scheme, is based on communications, meaning one terminal needs to send something to the other terminal, even if that something is a 0-1 signal, permission to trip, right? Then the latency of that channel adds up to the trip time. So if your channel is, takes 10 milliseconds to send information from one end to the other, your trip time would be 10 milliseconds plus something, right? It cannot be faster than the channel. So I would say, on average, for high performance relays based on 60 hertz, you could count on between one cycle, maybe 3/4 of a cycle, to cycle and a half. Now, it's not a fixed number because, depending on the fault resistance, depending on the load, depending on many things, the conditions would be more positive or, better for speed or worse for speed. But, cycle 2 cycles. With traveling waves, we see operation from the differential, traveling wave differential, on shorter lines on the order of 1 millisecond. The directional comparison scheme operates in 2 milliseconds, 2-3 milliseconds. And so those are the times we see. We went from, say, cycle and a half to 2 milliseconds. That's a big improvement. On top of that, you have this independence of the sources. One of the utilities that are using a lot of those relays, they use them because they have a lot of wind generation. And to your question about how they are used, normally use 2 sets of relays, so primary and backup, or system A and system B, independent. And they installed those relays as the third set. So you have system A, system B, and system C. So let's call the traveling wave relays as system C. In 99% of cases, system C is the first to trip, and it trips in 1 to 2 milliseconds. And that's not theory, that's not hope, that's not an expectation. That's what we see in the field, every 2 weeks when the fault happens, right? We have dozens and dozens of field cases when they show how well that technology works. Those cases become kind of boring and repetitive because they all start to look the same. But that's good. Boring is good in this business.
Any more questions? No? Yeah, how about, maybe one last question also. From what I understood, basically the algorithm that you explained, all of them were two-ended methods. So do you have single-end method implemented or not? So what's your comment on that?
Yeah, so they are double-ended because the differential requires the currents to be exchanged. So that's direct fiber. And the traveling wave directional works in a pilot scheme, meaning that 2 relays, one needs to say IC forward, so they communicate to tell each other IC forward. If both of us see a fault as forward, it must be between us, so we trip. The single-ended method that we have in this relay is called TD21. So it's the one based on incremental quantities, and it works kind of like distance. That element requires a strong system behind the relay. If it operates between 2 and 5 milliseconds, which is extremely fast. I think the fastest we saw was 1.5 milliseconds, which is just amazing. And it operates without the channel. However, that element requires a relatively strong source behind the relay. Wind and solar are not strong sources, so that element is not going to work in those systems. People are dreaming about traveling wave distance, meaning based on traveling waves and only using local voltage and current without communications. There is a long list of obstacles to making this practical. Actually, the one of the papers, it's not listed here, but one of the papers that I wrote with Dr. Schweitzer, it kind of catalogs all those obstacles. Maybe one day we'll be able to solve them, maybe not, but I would say it's extremely difficult to build a single-ended protection function that would work on traveling waves. So yes, you know, switching to communications is always a good way. Today, communications channels are cheaper than they used to be. They are digital, they are low latency. It's a no-brainer to migrate your schemes to be based on communications, especially if you have wind and solar and your 60 hertz based traditional protection is running into trouble.
Thank you. Thanks a lot. We really appreciate. So that was very informative talk. So we really appreciate that. Once again, give a round of applause for
Thank you for this opportunity.
Thank you. Okay, have a great day and hopefully see you sometime soon.